harder sketching. So here we're going to look at how we can sketch some curves that are in the form of a rational function. So something like f of x equaling p of x over q of x, where we had some kind of polynomial over another polynomial, and we get some rational function here. So when we look at some more difficult examples, we have a lot of things that we can consider when sketching the graph. The first thing we want to consider is any restrictions on the domain and range. So these are values that x or y could not beat, and usually some giveaways are when you don't want to be dividing by 0, when you have square roots where they have to be greater than or equal to 0, and also when you have constants in the numerator, that tells you that y can never be 0 as well if there's no extra terms. There's just a couple of examples. The second thing we can do is to find x and y intercepts. And we can find our x and y intercepts, so we can find x-intercepts by just setting y equal to 0 and solving for x. And we can find y-intercepts by setting x equal to 0 and finding answers for y, and that's going to help us as well. The third thing we can do is to find any stationary points and determine their nature. Another thing we can do is to find any other asymptotes that there might be that we haven't accounted for with step number 1. And this could be possibly an oblique asymptote. And another thing we could do is to check limits of the function as x approaches plus or minus infinity. And as a last resort, you could always test some values into the function and just see what's going on. Now, some of the hardest things to do are find asymptotes sometimes. And we're going to write some things down which might help us. So if we do have a function in the form f of x equals p of x over q of x, we're interested in the degrees of the polynomial. So, for example, if we had y equals x squared plus 2x over x cubed minus 4, the degree of the numerator is 2, and the degree of the denominator is 3, because we're just looking at the highest powered terms and seeing what those powers are, and that's how we can determine what degree they are. And this is going to help us in checking if we need any asymptotes to find. Okay, so we're going to make some rules. We're going to say if the degree of the numerator is less than the denominator, that means that y equals 0, or the x-axis, is an asymptote. If the degree of the numerator equals the degree of the denominator, there's going to be an asymptote at the ratio of the leading coefficients of the numerator over the coefficient of the denominator. if the degrees are equal. So an example of that might be if we have y equals x squared plus 3 over 2x squared minus 1. Here the degrees of the numerator equal the denominator because they both have a highest power of 2. And here the asymptote would occur at y equals the ratio of the leading coefficient. So 1 is the one for the numerator and 2 for the denominator. So there'd be an asymptote of y equals a half in this case. So that's where the asymptote occurs if the degrees of the numerator equal the degrees of the denominator. Now, if the degree of the numerator is greater than the degree of the denominator, there is no asymptote unless the degree of the numerator is only just 1 more than the denominator. So if n actually equals d plus 1, there is an asymptote. And the asymptote must be oblique. And if it's oblique, we can use long division to find it. And there's other ways, but we'll look at how we can find it with long division. All right, so let's look at an example. Let's look at y equals 3 outside of x plus 2, outside of x minus 3, all over 2 outside of x plus 1, all squared. Now, we can make note straight away that x can't equal minus 1 because we'll have minus 1 plus 1, which is 0. 0 squared is 0, and 2 times 0 is 0, so we'll be dividing by 0. So that must mean there's an asymptote at x equals minus 1. So let's draw our xy axis so we can start sketching in some things we know. So we know there's an asymptote at x equals minus 1. Now, we can find some intercepts if we make x equal to 0. So let's go ahead and do that. So we'll just have 2 minus 3 and 1 squared. So let's have a look. If there's any y-intercepts, so we'll get minus 18 over 2, which is minus 9. So we get a y-intercept of minus 9. So somewhere down here we know there's a y-intercept. We can make y equal to 0 to see if there's any x-intercepts, which just means we don't even have to consider the denominator because we'll just times it over. It'll end up being 0. Dividing both sides by 3, we'll know that x has to be equal to minus 2 or 3. So we know there's 2 x-intercepts, one at minus 2 and one at 3. Now, let's expand all of this out just so we can maybe see things a bit clearer. So we expand it out, we'll get 3x squared, then x times minus 3 will be minus 3x, plus the 2x we'll get minus x, and times the 3 we'll get minus 3x. Then 2 times minus 3 is going to give us minus 6, times the 3 is minus 18. All over, well, we're going to get x squared times 2 is 2x squared, plus 2x times 2, which is 4x, and plus 1 times 2, which is 2. And the reason we did this is now that we can look at the degrees of the numerator and the denominator, and this has a highest degree of 2, and so does the denominator. So they have equal degrees. And the rule was when the numerator and denominator have equal degrees, the asymptote occurs of y equals the ratio of the coefficient of the highest degree in the numerator, which is 3, over the coefficient of the highest degree in the denominator, which is 2. So now we know that there's a horizontal asymptote at y equals 3 on 2. So we have this 3 on 2, and we have a horizontal asymptote here. Now, what we want to do is we want to check what happens as well. We might have enough to graph. We have enough to graph this section here because we know it's cutting here, and we have an asymptote here and here. So safe to say we've got enough here. So we're cutting here, and we've got this behavior like this. Now, we know there's no cuts over here, so we know we have some kind of, and we have a cut here, but what's going on? We have an asymptote. Does it approach the asymptote from underneath, or does it actually cross the asymptote, then come back and approach it from above? Does it approach it from below or above? Now, what we can do is we can just sub in a really small value here just to see what's happening. Is it going to be below a 3 on 2, or is it going to be above 3 on 2? So let's go ahead and sub in a big value on the calculator. So we're going to put in y equals, you pick any big value you like. So let's go minus 1,000. So we'll have 3 outside of minus 1,000 squared, minus 3 times minus 1,000, minus 18, all over 2 times minus 1,000 squared, plus 4 times minus 1,000 plus 2. And plugging all that in the calculator gives us 1.5044, which actually means that it's approaching it from above because it's a bigger value than that. So now we know our graph approaches this asymptote, cuts the minus 2, goes above this asymptote, and then actually comes back and approaches it from above. And we get something like that. We also could have went and found a stationary point if we derived this, and it would have told us this point here, but this was enough to graph it out. So let's look at one more example. Let's look at y equals x squared over x minus 1. So straight away, we can know that x cannot equal 1, because then we'd be dividing by 0. So we've already got something that we can graph. So at the point 1 here, we've got a vertical asymptote already. Now, let's see if we can find any x and y intercepts. So if we want any y intercepts, we can set x equal to 0 to find any y intercepts. So we'll have y equals 0 squared over 0 minus 1. So we're just going to get y is equal to 0, which we know we're going to have an intercept at the origin. And doing the same thing for x, if we make y equal to 0, we'll just have x squared over x minus 1 times both sides by a denominator, so we just get x squared equals 0, which means x equals 0. So that's the only intercept at the origin. Now, let's look at horizontal asymptotes in terms of looking at the degrees of the numerator and the denominator. So the highest degree is 2 in the numerator and the highest degree is 1 in the denominator. And we did say if the degree of the numerator was greater than that of the denominator, there was no horizontal asymptotes unless that degree was only bigger by 1. And in this case it is. So if it is bigger by 1, we actually would like to do some long division to find an oblique asymptote. So let's go ahead and do that. So we've got x squared divided by x minus 1. So how many times does x go into x squared? Well, that goes in x times, and then we multiply it back out. So x times x is x squared, and x times minus 1 is minus x. So let's just throw in our 0x and 0 if needed. Do the subtraction, x squared minus x squared is 0, and 0 minus minus x is plus x. And how many times does x go into x? Well, that goes in once. Multiply it back out. So we get 1 times x, which is x. We're just going to drop down the 0. And 1 times negative 1, which is negative 1. Do the subtraction. X minus x is 0. 0 minus minus 1 is 1. And that's our remainder. So now we can rewrite y as x squared divided by x minus 1 equals x plus 1 plus our remainder over our divisor. So this function is equivalent to x plus 1 plus 1 over x plus 1. And why does that help us? Well, that helps us because now we can analyze the limit as x approaches infinity or negative infinity, or both. So we want to analyze the limit as x approaches plus or minus infinity of x plus 1 plus 1 over x minus 1. And looking at values of infinity, if we have 1 over infinity minus 1, well, infinity minus 1 is just infinity, and 1 over infinity is 0, so all of this tend towards 0, and the limit becomes x plus 1. And doing the same thing with negative infinity minus 1 is just negative infinity, and 1 over negative infinity is also 0, so it's also approaches x plus 1. And this is in fact our oblique asymptote, y equals x plus 1. So we can go ahead and graph that in. So we get 1 and minus 1 for the intercepts, and this is our oblique asymptote. Now, what we have, we know the curve is cutting the origin, and if it's approaching these asymptotes, we're going to have to, we know the graph is coming down here and here, because we know it has to be inside this point because we have an intercept here. And because there's only one intercept, the graph is going to have no choice but to just touch at this point, because there's no way that it could come up here and then down, because we know that this is the only intercept. So we know that it has to come up here, touch, and come down. There's no other way to draw that. And since it's inside this here, it's very likely that it's inside up here as well, because it has to be approaching. So we can just go ahead and draw that in, and you could test some values if you had to, but we're pretty confident that this is be the case, approaching these asymptotes up here as well.